Let us discuss about one of the most important concept in fluid dynamics, that is Bernoulli's theorem. We can state about it that this is a theorem about conservation of energy for a flowing fluid from one end to another in a streamlined flow. When a fluid is flowing in a streamlined manner, then from one end to another, when we apply energy conservation, the mathematical analysis is deduced by the concept of Bernoulli's theorem. Let's analyze a practical situation based on which we'll also derive a relation for energy conservation, which we term as Bernoulli's equation. Say we are given with a flowing fluid line, and say one end, if we talk with respect to ground, with respect to normal ground, say one end is located at a height h1, other end is located at a height h2 above the ground, and say the cross-sectional area at these ends are a1 and a2, say if this end 1, this end 2, and the fluid which is getting into the fluid line is at a speed v1 and due to the pressure p1 acting on it, and at the other end if the fluid pressure is p2 and the fluid velocity which is coming out is v2. As we know well that if cross-sectional area reduces, flow velocity increases. But say if pressures are P1, P2, V1, V2 are the velocities and E1, E2 are the cross-sectional areas, then in this situation, we apply a basic work energy theorem for the flowing fluid in flow from end 1 to end 2. Let's apply this. We use work energy theorem for a volume delta V of fluid from end 1 to end 2. Let's see what we'll be getting. If we talk about end 1, the mass of fluid having a volume delta V can be written as rho delta V if rho is the fluid density. Then the kinetic energy, initial kinetic energy at end 1 can be written as this initial kinetic energy. We can write half mass is rho delta V multiplied by V1 square. This is the initial kinetic energy. And if the pressure P1 is pushing the volume delta V into the fluid, the work done onto the fluid can be written as plus P1 delta V, and the mass rho delta V is pushed from end 1 to 2, so its height level with respect to ground is increased by h2 minus h1. So in this situation, as it is going up, gravity will be doing a negative work on the fluid, so we can write it minus the mass is rho delta V multiplied by G into h2 minus h1. We use mgh, and this must be the kinetic energy of fluid at the other end, but here a pressure P2 is acting. So when the fluid will come out, this P2 will be opposing the fluid which is coming out. So another negative work is done in ejection of liquid against the pressure P2. So we'll write it minus P2 delta V. This must be the final kinetic energy with which the fluid will eject out from the other end. So it can be written as half rho delta V mass of the fluid, as we are taking only delta V volume, multiplied by V2 square, which is the final kinetic energy. Now in this expression, the term delta V can be cancelled from all terms, and now if we simplify it, let's continue on the next sheet. Now here if we further simplify the expression, you can see we'll be getting it half rho V1 square plus P1. In this expression, we'll be getting minus rho G H2 plus rho G H1 minus P2 is equals to half rho V2 square. Now if we slightly rearrange these terms, For first hand, all the terms if we take on left hand side, and for second hand we take all the terms on right hand side of equality, you can see we'll be getting half rho V1 square plus P1 plus rho G H1 is equals to half rho V2 square plus P2 plus rho G H2. This is the expression we are getting. So here if we just carefully analyze, we can write at all sections of the flowing fluid body, we can use, in this situation we can write half rho V square plus pressure plus rho GH. This term will remain constant, as here we have written the work energy theorem for only two ends. So we can see these terms, summation of these terms are coming out to be a constant. So in this situation we can state the first term we can directly see half rho V square, where rho is the mass per unit volume. So half rho V square can be simply written as kinetic energy per unit volume of the fluid. And in this situation if we talk about the last term, it is mg, as this can be written as gravitational potential energy per unit volume with respect to given reference. Here reference of potential energy, we have taken the ground level. So obviously as these two terms are giving us the energies per unit volume for the flowing fluid, this P is also given a term pressure energy per unit volume of the flowing fluid. So whenever a fluid flows in a given manner, we can simply state at one point we can define three different kind of energies per unit volume for the flowing fluid, that is kinetic energy, pressure energy and gravitational potential energy. And for a flowing fluid, the sum of these three always remain a constant, and this equation we term as Bernoulli's equation. And in various numerical applications we are going to use this equation, as it is one of the most useful mathematical expression for describing the analysis of fluid flow.